Welcome to solverfy.
So in this problem, we have a motor that's spinning some unbalanced mass, and it is supported by a beam. So we have something, we have a beam here, simply supported, a motor on the middle of it, generating some force. And we're told that from just strength of materials, which you may or may not have had that class already, the deflection of a beam that's simply supported like this at its middle is the load, P, times the length of the beam between the supports cubed, divided by 48 times the Young's modulus times the area moment of the cross-section. And this is exactly why I don't like to use I's and J's for I'd like to use J's for mass moments and I's for area moments, because when you start getting into combining structures that vibrate, then you got to worry about which moment are you talking about. And the fact that a lot of times they call this a moment of inertia in fact they even did it in this book. It says the moment of inertia of the beam's cross section or area is, well, this has nothing to do with inertia. So I really hate that that vocabulary. I just call it an area moment, and that's what it is. It's a moment of the area, and it has nothing to do with the mass or the inertia of the cross section. It purely has to do with the shape. So anyway, that's what this is. And again, given the shape of the cross-section of this beam, you could figure out what that is, and given what the material that the beam is made out of, you can get that. So we want this spring constant. So that's P, the force, divided by the deflection at the middle. And so we can just, let's see here, multiply through by this, and we get that the spring constant is 48 EI over L cubed. And so we can see that, well, one thing you can check is that if L gets very small, the spring constant gets very large, because you're basically pushing very close to the supports. And that makes sense. So the natural frequency, so we have this block M here. The natural frequency is just the stiffness divided by the square root of the stiffness divided by the mass. So that's simply this. We have a rotating unbalance on this, and it has a mass. The unbalanced mass is little m, the eccentricity is r, and the rotation speed is omega squared, which is also the excitation frequency. Now we can substitute all of this stuff in to find the amplitude of oscillation, and that's what we're looking for. So we can sub all this stuff in and do a bunch of algebra, a bunch of algebra math to get this into a simple form like this. And it turns out we have mr, the eccentricity, L cubed, times the the excitation frequency squared, all over 48 EI minus the mass times the length cubed times the excitation frequency squared again. One thing you can check here is, say the excitation frequency squared gets really big. That means this dominates this, so that goes away. And then this would cancel with this, and this would cancel with this, and then our amplitude would simply be the ratio of the unbalanced mass to the total mass times the eccentricity. So that's what, as the forcing frequency gets very large, we asymptote to of that value. So we start here, come up, go to infinity with natural frequency, and then come back down and asymptote to a value here. That's actually the ratio of the mass times the eccentricity. Let's see here. If L goes to 0, then Y goes to 0, because that means you're pushing on this rigid support here. So that makes sense. And we can see how, as we change EI and L around, we change the natural frequency, and we could, when this thing is 0, that's when resonance occurs. So we could figure out the forcing frequency here that excites resonance is simply that's at omega squared is simply going to be 48 EI all over ML cubed, which makes sense because that is the natural frequency squared.